compressing large amounts of information and being able to store them in less space, transmit them over networks with less bandwidth, and in general, be able to hold on to more information with less requirements is a really important tool to have available in computer science. Sometimes we'll be able to get by with reducing the size of our data by losing some information about it, but sometimes it's really important to get exactly accurate recreation of that information that we compressed. And we need a lossless compression method in those cases. One lossless compression method is Huffman coding. So we'll look at Huffman coding as a technique using a binary trie to be able to create our encodings. We'll focus on the problem of text compression. So if we have some text or some binary data, we might want to change our representation of it so that it takes up less space to store, less time to transmit over a network, and can be reconstructed exactly from that compressed representation so that we don't lose any information from the original data that we compressed. For example, if we wanted to compress the string containing the word abracadabra, we see it's got some repeated letters, and we see that it doesn't have very many total letters in it. But using the ASCII coding, it would take 11 bytes or 88 bits to transmit that word abracadabra or to store it. We could do much better if we just look at the fact, as mentioned before, that it only uses part of the alphabet. So since it only has 5 total symbols in it, our alphabet could be communicated separately, sending A equals 000, B equals 001, and so on, and then we would only need to use 3 bits of data for each character in the message, reducing us down to 33 bits for the total message. But contriving these kinds of alphabets, transmitting them separately, and using a standard set of bits for the data may be unnecessary. We can actually reduce lower than that amount. For example, we could use only the number 0 for A, and we could use fewer than 3 bits for some of the characters, and that might allow us a better size in our result. This, for example, when we limit to this encoding shown here, only requires us to use 23 bits to transmit that information. But we would have to actually have a scheme for coming up with the mapping that would allow us to use that reduced space. It's pretty easy to come up with any random encoding that we'd like to that might make our data shorter, but we also need that encoding to be decipherable. We need to be able to undo that encoding when it arrives at its location or when someone goes to open that file. So some examples of ones that may not be perfectly decipherable are these here for encoding E, T, N, I, and S. So it could be representing the word tennis, or it could, the other encoding here could represent tennis, but it could represent tense, and could represent the word ten with S and T, and many other possibilities. So we need an encoding that is easily decipherable and that can always come out to the correct result in the end. We don't want our users guessing at what the data is that we've stored for them. So we can use prefix codes to come up with a scheme where it is always deterministic to decode the information that we've encoded and compressed. We have to make sure, however, that no prefix of a code word is another code word. This gives us uniquely decodable strings. For example, we have here 2 encodings that are uniquely decodable and 1 encoding which is not. The one encoding is not uniquely decodable because you can see that A is 0, 0, but the D starts with 0, 0. So when we see the sequence 0, 0, we can't tell for sure whether that's an A being represented there or whether it's the start of the letter D. So on the other hand, for the other ones over here, the furthest left, A is 0, 0, yes, but no other code starts with 0, 0. So we know when we see 0, 0, that's an A. It couldn't be a partial value of another key. And likewise, the other ones here, though they get very long, where A is 1 and B is 0, 1, and C is 0, 0, 1, those are all, however, unique because once I see a 0, 1, I know to stop. I know that it's B, and I've decoded that particular letter. But we want to come up with good ones. So we can come up with these kinds of prefix codes by using a trie, and in fact a binary trie, where 0 is the left child and 1 is the right child. So if I needed to encode A, B, C, D, E, and F here, I could build a trie in which all of those are leaf nodes, all of those letters are leaf nodes, and along the way I'm assigning single digits, binary digits to them. So this way is how A got to be 0, 0, because it is left and left again. B was left, right, left, and that gave it 0, 1, 0, and so on. This does not, however, tell us how to build that trie and how to decide which of our letters gets which key, in particular which of our letters gets which length of key, because you can see that A is shorter than D, which uses 4 bits here. So taking a look at this longer string with some repetition of characters, we can come up with the scheme of Huffman coding. In this, we count how many times each symbol appears, and we use those repetitions to decide how long the keys are going to be. So we'll store those counts as a frequency in a pre-made trie node. Each of them can be thought of as a trie with just a single node in it right now, and we're going to merge those different nodes to make one big trie. The way that we'll do that is we'll look at the ones with the lowest frequencies first. So for example, A and H had the lowest frequencies in our sequence there. So we will combine those two into a larger subtrie by creating a parent node for them and making one the left child and the other the right child. And then we will sum the frequencies of the two children to give the parent its value. So A had 3 and H had 2, so the sum of those would be 5. This will build the tree bottom up. That means that A and H will have the longest sequence of key, and they are the ones that will show up the least often. So we'll use short keys for things that show up more often. Our A and H subtree gets combined with C to make a larger subtree and creating a parent node for them. And then E and I are the most frequent. So again, we want them the highest up in the tree. We'll take the two of them, combine them into a subtree, and sum them to get 15 for the parent's value. And then we'll take that subtree and combine it with the subtree that contained the other letters, creating one root node with a frequency count of 25. And then we walk through that tree assigning zeros to the lefts and ones to the rights. So that, for example, A, the furthest down, gets 0, 0, 0. So it will be one of the longest keys, but it shows up the least often, so we won't use much space to store the A values. And E and I get keys that are only 2 digits long. And because of the fact that we have constructed things in this left-right way with the prefixes, we know that no key will have a value that's a prefix of any other key. Once I've gotten to 0, 1 to represent C, C is a leaf node. Nothing else falls below it, so nothing shares a prefix that is C's key. So the code construction in our Huffman coding uses a greedy algorithm. It chooses the best local solution at each step by choosing those lowest frequency nodes and then the next higher frequency and next higher frequency. However, even though greedy algorithms don't always produce globally optimal results, meaning the best possible result, in the case of Huffman coding, it does yield the best overall solution. Its design allows for us to get these optimal prefix codes where we will come out with the shortest resulting encoding and use the least possible data because of the design of the Huffman coding, that we give the most frequently occurring characters the shortest keys. When we combine those two subtrees with the lowest frequency, we could use fast operations like we've seen before with priority queues, for example, where we can get the minimum value node, the next minimum value node, and so on. One note is that Huffman codings are non-deterministic if you have multiple characters with the same frequency. We have to make a choice between those, but there are good schemes for coming up with a single form of how we would make those choices, such as alphabetical ordering. We will have to transmit a little bit of information with our Huffman codings to allow the information to be decoded, because there's no way for a user to necessarily know that 0, 0 is a particular letter. We have to transmit at least enough information to them that they can come up with the same trie that we came up with and be able to build those keys and decode the information. But it will be compressed and it will be smaller than it originally was, as long as the amount of information that we have to send them about the frequencies is smaller than the amount that we're saving.